In today's video, we are going to go over 5 different examples for the buoyant force in Archimedes' principle. Now, before we get started, please don't forget to subscribe to our channel, Step by Step Science. Please support our channel. Subscribe, click the notification bell so you don't miss anything. Leave us a nice positive comment, give us a thumbs up, and don't forget to share this video. And in addition to that, we've made a bunch of other teaching and learning materials which you can find at our Teachers Pay Teachers website, where you're looking for example problems with solutions, puzzles, online labs that you can do. It's all there. The link is in the description below. And let's get started with example number 1. Example number 1 says that we have this copper cube, which is 15 centimeters on each side. And we are going to take that copper cube and we are going to hang it from a spring scale, and we are going to put that copper cube in water like that. And we want to know, when it's placed in water, how much will the cube weigh? Now you can see I put weigh here in quotation marks because really when we weigh something, we often weigh it in air. That's what we think of as the weight. So this is going to be the apparent weight when that copper cube is in water. And now I told you that the density here of copper is 8,940 kilograms per cubic meter. So what we need to do is we need to figure out what the buoyant force is going to be, because the weight is pulling down. You can see that Fg, that's the weight of the object, that copper cube, and we have the buoyant force because it's in air, and that pushes up in the opposite direction. So that means if we hang it from a spring scale, the force on the spring scale, Fs, is going to be the weight minus the buoyant force. The weight pulls down and the buoyant force pushes up in the opposite direction. We can get the weight from Newton's second law, Fg equals mg, and we can get the buoyant force from this equation, which is that the density of the fluid, which is water in this case, is times the acceleration due to gravity times the volume of the object, or the volume of the water displaced, because they're the same, will give us the buoyant force. Now, the weight of the object, we need to get the mass. Now, I gave you the density and the volume, so you can get the mass from the density equation, which says that the density of copper is equal to the mass divided by the volume. We can rearrange that. We get the mass is equal to the density times the volume. If we plug the values in, we get that the mass is 8,940 kilograms per meter times, and we got to convert this into meters because this is centimeters. That's 0.15 meters. We cube that, and we get that the mass of that cube is going to be 30.2 kilograms. And now to get the weight is 30.2 times 9.81 from this equation right here. And that gives us that cube weighs 296 newtons. So that is the weight. That's this value we need. Now we need the buoyant force. We can calculate the buoyant force from our buoyant force equation, which says that the density of the fluid times g times the volume is equal to the buoyant force, which this is the density of water, 1,000 kilograms per meter cubed. This is acceleration due to gravity, g, and this is the volume, once again, in meters. We got to cube it, and we get that the buoyant force is 33. So now we have the weight, we have the buoyant force, and the weight on the spring, the force on the spring scale is going to be the weight of the object, which pulls down, the buoyant force, which pulls or pushes up, and we get that cube in water, the apparent weight, is 263 newtons. That is the end of example number 1. And now we can go on to example number 2. And example number 2 has to do with the buoyant force on the body. Now, we don't often think about the buoyant force in air, but we are in air, which is a fluid, and it does exert a buoyant force. It's not very high, as you'll see, because density of air is not very high. But we can figure out the buoyant force on a person who has a mass of 80 kilograms. Here's the density of the human body, which I just looked this up. I found a few different answers, but I got this values. And this is the density of air. And we can get the buoyant force on that person is that the density of air, because you're in air, times g times the volume. Now, once again, I didn't give you the volume. I gave you the mass this time and the density. So you can get the volume of a person from the density equation. The density of a person equal to the mass divided by the volume. The volume would be the mass divided by the density, and then that's 80 divided by 985 kilograms per meter cubed. You can see the kilograms cancel. You're left with 0.081 meters cubed. We can plug that into this equation, which is the density, the acceleration, and the volume, and you get that the buoyant force, your weight really decreases by 1 Newton when you're an 80 kilogram person approximately. Now, is that a lot? I mean, it's not a lot, but let's just see what that would be maybe in pounds. Okay, this is the buoyant force in newtons, and we can get the mass of that amount of weight in gravity, due to gravity, by taking Newton's second law, and we can take the mass is equal to the force. This force is due to gravity, therefore the acceleration is 9.81, and we get the mass is 0.105 kilograms, which is like 105 grams. How many pounds is that? Well, we can use this conversion factor because 1 kilogram is about 2.2 pounds, and we can see when you're in air, you weigh a little less. You weigh 0.23 pounds less. Now, it's not very much, but if the air was to go away, then you would weigh more, and that wouldn't be good. But if the air was to go away, then you would also be dead, so it wouldn't really matter. Okay, so there you go. That's example number 2. Now, example number 3 is we have this object, and when we measure it in air, when we weigh it, it weighs 12.5 newtons. Then we're going to place it in water, and its weight, its apparent weight, is 8 newtons. We want to know what is the volume of the object. Okay, everything has a weight on Earth. When we put it into water, it still has that weight, but we say it doesn't weigh the same because there's the buoyant force which pushes it up in the opposite direction. Okay. Now, the buoyant force is the force in air minus the force in water, and therefore the buoyant force is 4.5 newtons. We can just subtract those two. We don't need to use the other buoyant force equation. We want to know the volume. So here's the buoyant force equation, and there's the volume that we're going to solve for the volume. And when we solve for the volume, we get the volume as the buoyant force divided by the density of the liquid that it's in, the fluid that it's in, which is water. So that says the density of water times G. And therefore, we get that 4.5 newtons divided by 1,000 times 9.81. So the volume of that object is 4.6 times 10 to the minus 4 meters cubed. That kind of corresponds to that buoyant force, like that, when we have those two weights in air and in water. Okay, that is example number 3. And now we can go into example number 4, which is a floating object. So this object is not submerged in water. It's floating, and we want to know, it's a piece of bamboo, we want to know what percentage of it is actually submerged in water. Okay, now the density of bamboo is 620, the density of water is 1,000. Now you might know this intuitively, or you might see that maybe it makes sense that the answer is probably going to be 620 and 1,000. That's right, it's going to be 62%. Right? If you had something that has a density of half of water, then half of it will be in the water, half of it will be above the water. But we can actually use the buoyant force to come up with the answer to that and see where we get that 62%. Because we know that the bamboo has a force of gravity acting on it, and if that object is floating, then we know the buoyant force is equal. Those two forces are equal to each other, the force of gravity and the buoyant force. And the force of gravity is the mass of the bamboo times G, which is equal to the buoyant force, which is the density of water because it's in water, times G times the volume of the water that is displaced. Okay, when something is floating, we use the volume as the volume of the water that's displaced. It's always the volume, but in this case, it's not completely submerged. Okay, so now we can put in here here you can see here's the mass of the bamboo. Okay, we don't know the mass. Okay, but here you can see we can substitute in the density of the bamboo from the density equation, that the mass is the density times the volume. And you can see that we have G on both sides. So we can factor out, we can cancel G. That means we're left with the equation like this: the density of bamboo, volume of bamboo, is going to be equal to the density of water times the volume that is submerged, which is the same thing of those two volumes are going to be the same. And we can, not the same, but we can take the ratio of the two. The ratio of the volume of that is submerged, displaced there, divided by the volume of the bamboo is equal to the density of the bamboo divided by the density of the water. And therefore, we can take that ratio and we can divide the 620 by the 1,000, and you get 62%, or 0.62 or 62%. So that means the bamboo 62% of it would be underwater. Okay, now we have the last problem, and the last problem is the hot air balloon problem. And the hot air balloon problem looks like this. We have a hot air balloon, okay, I put here weather balloon, and it wants to lift a payload of 75 kilograms, okay? And the balloon, we're going to take into account the fact that it has a helium balloon, and the balloon actually has some mass. So the mass of the balloon is 1.25 kilograms. This is the density of air. This is the density of helium. And we know that the buoyant force has to lift those things up. So it has to be more than the weight of the helium. Now, I didn't put He here. This is not hydrogen. This is helium, H for helium. Then this is the mass of the payload, or the weight of the payload. And this is the weight of the actual balloon. Now, we know the buoyant force is the density of the air times the volume times G. Okay? We have a G in all of these terms. We can factor that, cancel that G out. And now we're left with this equation, which is the density of air times the volume is equal to, okay, density of the helium times its volume, and the mass of the payload and the mass of the balloon. Now, I'm going to do two things, because we want to solve for the volume. We have two volumes here. They're the same volume. So I am going to subtract this term from both sides to get it to the other side, and I'm going to factor the volume out. And therefore, I get that the volume that the volume times the density of air minus the density of helium, because I subtracted this from both sides, so this makes this a negative term, is going to be equal to the mass of the package times the mass, not times, but plus the mass of the balloon. And then I'm going to solve for the volume, which means I'm going to divide both sides by this term, the density terms here. And I get that the volume of the balloon is equal to the mass of the package plus the mass of the balloon, which were both given, divided by the density of the air minus the density of the helium. This is helium again. All right, and those are given too. So we know if we plug those values in, that we end up with just about 69 meters cubed. So in order at the surface of the Earth for a balloon to lift up itself and the package that and the helium that's in the balloon, because you got to take that into account. Here we did. And you're going to need a balloon that has a volume of about 69 cubic meters. Okay? So there you go. We did 5 excellent examples covering a range of possibilities for buoyancy and Archimedes principle. I hope that you found that video helpful. If you did, please don't forget to do all of the following 5 things. Support our channel, Step by Step Science. Please subscribe. Click the notifications bell so you don't miss anything. Leave us a nice positive comment, a thumbs up, and don't forget to share this video. Thank you so much for watching. We will see you in the next video.